So our topic for today is all about heat transfer. Our topic outline is conduction, convection, and radiation. Learning outcomes. Develop an understanding about heat and temperature and its applications. Develop an increased awareness of the relationship of heat and matter. Interpret and solve simple and practical problems using the fundamental equation, heat and temperature. So what is temperature? Temperature is a measure of how hot or cold a substance feels, and it is measured in degrees Celsius or Fahrenheit. Temperature is measured of the average kinetic of the particles of a system. So what is heat? What is heat transfer? Well, heat is a form of energy which is called a thermal energy, while heat transfer happens because of a temperature difference. Heat is a form of energy that derives its origin at the molecular scale. Hotter and colder substances having high temperature or low temperature with respect to a reference matter. There must be difference in temperature of the substance to have heat and energy transfer. If the object has big mass, it also has big thermal energy and subsequently amount of transferred energy increases. Since it is a type of energy, we use joules or calories as units of the heat. Heat transfer. Scientists in the late 18th century finally decided that all body must contain an invisible fluid which is called caloric. Caloric was assigned a variety of properties which proved to be inconsistent with nature from how to form. The flow of heat is called circulation. For example, matter has waves and could not be created or eliminated. But the most important property was that calories flowed from the hot blood to the cold one. Calorie provided a very useful way to think about the heat. Heat transfer. Heat always moves from warmer place to a colder place. Hot objects in a cooler room will cool to room temperature. Cold objects in a warmer room will heat up to room temperature. So temperature difference, the driving force for the heat transfer. So when two objects with different temperature, heat transfer will occur. We call this temperature difference as driving force. Cooler, more dense fluids since warmer, less fluids. So heat transfer happens when matter with high temperature is exposed to a lower temperature. So it is a driving force. Next is thermal energy is associated with the translation, rotation, vibration, and electronic states of the atom and molecules that comprise matter. So this is what happens when the driving force happens. The molecules are vibrating. That's why they are all moving to the colder place. Next. So thermodynamics versus heat transfer. Thermodynamics is concerned with the amount of heat, work transfer, and it gives no indication about rate. While heat transfer helps to determine the rate which at energy is transferred to or from a system due to temperature difference. Thermodynamics deals with the equilibrium states of matter and precludes the existence of temperature gradient. Heat transfer temperature gradient must exist, and such heat transfer is non-equilibrium process. Thermodynamics does not provide any information of the nature of interaction and the time rate which this interaction occurs, while the heat transfer have a distribution within a region of matter. So, law of thermodynamics. First law is Conservation of energy. Energy cannot be created or destroyed in an isolated system. Energy balances are critical to master. Then second law is entropy of efficiency. The entropy of an isolated system always increases and can be useful in calculating the efficiency of a system. Four particles over here, and then it will move this and it will become hotter as it moves back, and it will cooler down again, and the heat will be remove from here. Next. So what is the relationship of heat transfer to thermodynamics? The first law with work equal to 0. Q is the positive toward the system, or WK is the positive away from the system. And derivatives of U, dE, is the positive when the system's energy increases. Where Q is the heat transfer rate and WK is the work transfer rate. The derivative is the rate of exchange of the internal thermal energy with time. The only work that occurs, Q is equal to P, derivatives of V over dt plus du, derivatives of U over dt. Constant volume process equation is equal to Q is equal to du over dt is equal to mc subset of P dt over dt. Constant pressure process is equal to Q equals to dH and dt is equal to mc subset of P dt over dt. H is equal to U plus PV is the alipati, and CV and CP are the specific capacity of volume and constant pressure. When a substance undergoing the process is comprehensible, the two specific heats are equal to CV is equal to CP is equal to C. Q is equal to derivatives of U over dt is equal to mc dt over dt. Since solids and liquid can frequently be approximated as being comprehensible, we shall often make use of it. If heat transfer were reversible, then the equation will be P ds over dt is equal to P dv over dt plus du over dt. This might suggest that Q can be evaluated independently for inclusion. However, it cannot be evaluated using Cs because real heat transfer process are all irreversible. Since the rate of heat transfer cannot be predicted using TDS, how can it be determined? If U, T were known, then when WK is equal to 0 would give Q, but UT is seldom to superior. The answer is that a new set of physical principles must be introduced to predict Q. The principles are transverse laws, which are not a part of such subject of thermodynamics. They include Fourier's law, Newton's law of cooling, and Stefan Boltzmann law. The important thing to remember is that the description of heat transfer is why that additional principle is combined first of the first law of thermodynamics. So these are the two so topic outline: conduction, convection. What do you call that? Three types of heat mode of heat transfer. So conduction. When we say conduction, within solids or stationary liquid. When we say convection, from surface to a moving fluid. And radiation is from surface to another surface. So conduction. Conduction in general is the process of transmission of energy from one particle of the medium to the other. But here, each particle of the medium takes a different position. In physical or chemistry, the meaning of conduction is understood mainly as the transfer of heat, energy, or an electric charge to a material. Conduction can occur in solid, liquid, or gas. So when heat is transferred via conduction, the substance itself does not flow. Rather, heat is transferred internally by vibration of atoms and molecules. So, like what I show earlier, there is a vibration of the molecules. Electrons can also carry heat, which is the reason metals are generally very good conductors of heat. Metals have many free electrons which move around randomly. This can transfer heat from one part of the metal to another. So, conduction, this is how it works. From solid to another solid. Then, convection. Convection is a heat transfer in fluids generally takes place via convection. Convection currents are set up in a fluid because the hotter part of the fluid is not as dense as the cooler part. Forced convection, where the fluid does not flow of its own accord but is pushed, is often used for heating. The initial heat between the object and the fluid takes place through conduction, but the bulk heat happens due to the motion of the fluid. So there is an upward buoyant forces on the hotter fluid, making it rise while the cooler, denser fluid sinks. So this is how it works. So the air is cold while the surface is hot. So the heat is going up while the surface is warm. The heat will go down. So next is radiation. Radiation of heat is the process where heat is transferred from one to another body without involving the molecules. Radiation is heat transfer by electromagnetic radiation such as sunshine, with no need for matter to be present in the space between bodies. The third way to transfer heat in addition to convection and conduction is the radiation, in which energy is transferred by the form of electromagnetic waves. The amount of energy an object radiates depends strongly on temperature. For an object with temperature Kelvin and surface area A, the energy radiated in time is given by the Boltzmann law of radiation. So this type of heat transfer does not depend on the medium. Even though there is no object, there will be a heat transfer that's going to occur. So this is a example of radiation. So from the sun, there is a heat and it's drying up the clothes. So real life application is this is a three mode of heat transfer that's happening at the same time. So conduction, where there is a gradient. Convection, which is a heat from the water, heat from solid to liquid. Then radiation is the heat from the fire that is going around the, around in the air. So these are the symbols for thermal energy. Energy associated with microscopic behavior of matter. Unit is joules or joules per kilogram. Temperature, a means of indirect assessing the amount of thermal energy stored in matter. T, Kelvin or Celsius. Heat transfer, amount of thermal energy transfer over a time interval. Then heat, thermal energy transfer per unit time. So Q and the unit is joules. Heat, heat, heat rate, thermal energy transfer per unit time and per unit length, QW. Heat rate per unit length, thermal energy transfer per unit time and surface area, Q prime W over M. Heat flux, thermal energy transfer per unit time and surface area, and generation rate per unit volume, the thermal energy generated in a material per unit time and volume. So conduction, this is the subtopic of conduction. So Barnstein Baptist Fourier, timeline, Fourier's law. So who is Baron Jean-Baptiste Joseph Fourier? He was born 1768 up to 1830. Joseph Fourier lived a remarkable double life. He served as a high government official in Napoleonic France, and he was also an applied mathematician of great importance. So at 1798 to 1801, he was with Napoleon in Egypt. 1814, he was subsequently prefect of the administrative of officer in France. So he was a government official. So and next is 1807. He worked on the theory of heat law. Then next is on 1822 he created Fourier law solution. The book was called Theorie analytique de la chaleur. So in the book of Theorie analytique de la chaleur, he formulated a very complete exposition of the theory of heat. So is the Fourier law. So this is Fourier's law, heat flux vector quantity equation. The empirical law, heat flux Q multiplied by Wm squared, resulting from thermal conduction, is proportional to the magnitude of the temperature gradient and opposite to its sign. If we call the constant of proportionality K, then Q is equal to negative K dt over dx. So this is the equation of Fourier's law. Q is equal to negative K dt over dx. So Q is the heat flux. To get the heat flux, you will need to solve for W over m squared. While negative K is the thermal conductivity, and to get that is, you need to solve for W over m times K. The heat flux is a vector quantity. Equation tells us that if temperature decreases with x, it will flow in the x direction, and Q will be positive. And if T increases with x, Q will be negative, and it will flow opposite the x direction. Either way, Q will flow from higher to lower temperature. So this is an example of a problem. The front of a slab of lead, K is equal to 35 over m times K, is kept at 110 degrees Celsius, and the back is kept at 50 degrees Celsius. If the area of the slab is 0.4 squared and it is 0.03 MK, compute the heat flux Q and the heat of transfer rate Q. So the solution is Q is equal to negative 3, 50 minus 110 over 0.03 is equal to 70,000 over Wm squared. So Q is equal to QA is equal to 70 times 0.4 is equal to 28 kW. So for your law, in a simple scalar form, so Q is equal to K, derivatives of TL, and L is the thickness in the direction of the heat flows, and Q and delta T are both written as positive quantities. We must remember that Q always flows from high to low temperature, and this equation is for one-dimensional steady state conduction. So one-dimensional equation, Fourier's law, involves two dependent variables T and Q. So Q net A is equal to Q net is equal to negative KA A squared T over A squared AX squared X. To eliminate the heat loss, Q net in favor of T, we use the general first-case statement for closed non-working system. So negative Q net A is equal to derivative of U over dt is equal to PCA d multiplied by T minus T ref over dt X is equal to PCA. So Fourier's law, general vector from Fourier's law, Q prime is equal to negative K T. So heat flux is, I said earlier, is W over m squared. K is thermal conductivity, and while this is a temperature gradient. So next, typical convective cooling situation. This is a heat conductor. Gas flow past a warm body. The fluid immediately adjacent to the body forms a thin slowed down region called boundary layer. Heat is conducted into this layer, which strips it away and farther downstream mixes in stream. We call such process heat away by moving fluid conduction. So heat convection, the physical process considered typical convection cooling situation. Cool gas flows past a warm body. The fluid immediately adjacent to the body forms a thin slowed down region called a boundary layer. Heat is conducted into this layer, which sweeps out the way of carrying heat away by a moving fluid convection. In 1701, Isaac Newton considered the convection process and suggested a cooling. The cooling. Isaac Newton is born in 1652 and 1726. He is known as a natural philosopher. He is the mathematician, physicist, astronomer, alchemist, theologian, and author. Widely recognized as one of the greatest mathematicians, physicists, and influential scientists of all time. He was the key figure in the philosophical revolution of the Enlightenment. Newton's law of cooling states that the rate of heat loss of a body is directly proportional to the difference in temperature between the body and its environment. The law is frequently qualified to include the conduction that the temperature difference is small and the nature of heat transfer mechanism remains the same. This condition is generally met with heat conduction, which is guaranteed by Fourier's law, as the thermal conductivity of most materials is only weakly dependent on the temperature. In convective heat transfer, Newton's law is followed for forced air system fluid cooling, where the properties of fluids do not vary strong with temperature, and it's only approximately true for buoyancy-driven convection, where the velocity of the flow increases with temperature difference. Finally, in the case of heat transfer by thermodynamics, Newton's law of cooling holds only for very small temperature difference. So this is the Newton's law of cooling. So this is the body overheating. T over body at T subset of body minus T infinite. So T body is the energy of the body, and T infinite is the temperature of the incoming fluid. So equation in terms of Q is equal to Q over A as Q is Ht body minus T T infinite. So this is the steady state form of Newton's law of cooling as it's usually quoted, although Newton never wrote such an expression. The constant H indicates that it is an average over the surface of the body without the bar. H denotes the local value of the heat transfer coefficient at a point of surface. The unit of H and constant H are W over m squared K, or joules sm squared kinetic. So this is the steady form of Newton's law of cooling, and it's usually quoted, although Newton never wrote. This constant H of the field coefficient of heat transfer coefficient. The bar over H indicates that it is an average over the surface of the body without the bar. H denotes the local value of the heat transfer coefficient at a point on the surface. The unit of H and constant H are W over m squared K, or joules over S times m squared times K. The conversion factor for any unit is 1 is equal to 0.0009478 BTU over J times kinetics over 1 over 8 Fahrenheit times 360 over H and times 0.3048 m squared and over f2 squared. Or simply, 1 is equal to 0.1761 BTU over H times f2 squared times Fahrenheit over W over m squared K. Newton somewhat oversimplified the convection when he suggested that the rate of cooling is proportional to the temperature difference. Actually, cos of H can depend on the temperature difference T body minus T infinite is equal to T. We find that H really is independent of the situation in which fluid is forced past the body, and T is not too large. This is called forced convection. When fluid was from a hot body or down from a cool one, H varies as some with power of T, typical as T to the power of 1/4 or T to the power of 1/3. This is called free or natural convection. If the body is not enough to boil a liquid surrounding, H will typically vary as T squared. For the moment, we restrict consideration to situation in which Newton's law either true or at least a reasonable approximation is given. The heat flux Q is 600, this is an example. So the heat flux Q is 6,000 Wm squared at the surface of electrical heat water. The heater temperature is 120 degrees Celsius when it cools by air at 70 degrees Celsius. What is the average convective heat transfer coefficient for constant H? What will be the heater temperature power if reduced so that Q is 2000 Wm squared? So the solution is constant H is equal to Q over T is equal to 6000 minus 120. 6,000 over 120 minus 70 is equal to 120 per meter. If constant H stays fairly constant as the heat flux reduced, then the T is equal to T heater minus 70 degrees is equal to Q over constant H is equal to 2000 W squared by all over 120 W over M squared is equal to 16.67 kinetics. So T heater is 70 plus 16.67 is equal to 86.67 Celsius. So we should have some idea of how large H might be in a given situation. The table below provides some illustrative values of H that have been observed or calculated for different situations. They are only illustrative and should not be used in calculation because the situation for which they apply have not been fully described. Most of the values in the table could be changed a great deal of varying quantities that have not been specified, such as surface roughness or geometry. So, natural convection in gases, 0.3 and vertical walls in air usually have a 4.3 constant H. 1 m diameter horizontal wire air have a 29 constant H. Natural convection in liquid 40 mm. OD horizontal pipe in water have a 570. 0.25 m diameter wire in methanol have 4000. Force convection of gases air at meter per second inside 20 m ID2 is 45, while the 30 m over 1 m flat plate is 80. Then water at 2 m over 60 m plate is 590. Aniline alcohol mixture at 3 m in 25 m ID2 is 2600. Water at 10 m inside 20 m and ID tube is 34,700. Liquid sodium at 5 m in a 13 m ID tube is 370 is 75,000. Boiling water doing fume boiling 300. In kettle is 4,000. At highest full boiling is 40,000. Doing convective boiling value is 10 to the power of 8 to 10 to the power of 6. Condensation in typical horizontal water tube flame but condensing between drop wires condensation in the water at 1 atm. Lamp capacity solution. We now deal with a very simple but extremely important kind of convective heat transfer problem. The problem is that of predicting the transient cooling of a convection cooled object. In the case when the body has almost uniform internal temperature, when internal temperature gradients are small, we can lump all of the heat capacitance in a single body temperature T is equal to P times T. With the reference of the previous figure is now familiar first law statement thermodynamics. So this is the first law that I have tackled earlier. And Q, you can get the Q by solving negative constant HA times T minus T infinite, which is Q is the surface area, while du over dt, du is always 0, while dt is while du is taken as the surface volume, which is you can get by d over dt multiplied by PCV times T quantity T minus T ref. So next is the general solution is logarithmic of quantity T minus T infinite equals to T over PCV all over constant HA plus C. If the initial temperature is T, then the C logarithmic is T this I minus T infinite the group PCV all over constant H is D time constant. The cooling of the body is given by T minus T infinite all over Ti minus T infinite is equal to E to the power of negative T over T. All of the physical parameters in the problems are now contained in this time constant T. It represents the time required for the body to cool to 1 over E or 37% of the initial temperature with difference above or below T infinite. The time constant can also be written as T is equal to NC, quantity 1 over constant HA, where M is equal to PV is the mass of the body. A body of greater mass or greater specific heat capacity will have a larger time constant, will take longer to cool. The quantity 1 over constant HA may be thought as a resistance, and in other words, a body with less surface or low surface takes longer to cool. The physical notice that the thermal conductivity is missing from T minus T infinity over all over Qi minus T infinity is equal to I to the power of negative T over T, and T is equal to MC quantity 1 constant all over constant HA. The reason that we assume that the temperature of the body is neither uniform, and this means that the internal conduction is not important. We see that if L, KD, is less than 1, the temperature of the body at any time, we name this constant HL all over K subset of T negative less than 1 implies that TBX T congruent to T congruent to T surface. Stephan-Boltzmann law is formulated by Austrian physicist Joseph Stefan in 1879 as the result of experimental study, and the same law was derived in 1884 by Austrian physicist Ludwig Boltzmann from thermodynamic consideration. So in 1864, John Tyndall presented measurement of the infrared emission by platinum filament and the corresponding color of the filament. The proportionality of the full power of the absolute temperature was deduced by Joseph Stefan in 1879 on the basis of Tyndall's experimental measurement. The meaning of the article is on the relationship between thermal radiation and temperature. The derivation of the law from theoretical consideration was presented by Ludwig Boltzmann in 1884, drawing upon the work of Aldo Bertolli. Bertolli in 1876 had derived the existence of radiation pressure from the principle of thermodynamics. Following Bertolli, Boltzmann considered an ideal heat engine using electromagnetic radiation instead of an ideal gas matter. So, radiation, heat transfer by thermal radiation. All bodies constantly emit energy by a process of electromagnetic radiation. The intensity of the radiation, the rate of this radiant energy flux depends upon the temperature of the body and the nature of its surface. Most of the heat that reaches you when you sit in front of a fire is radiant energy. Radiant energy browns your clothes in an electric toaster, and it warms you when you walk in the sun. Objects that are cooler than the fire, the toaster or the sun, emit much less energy because the emission of energy or radiant heat transfer by cooler bodies is connected to the convection conduction. Heat transfer process with high temperature or with conduction and convection suppressed by a vacuum involve a significant fraction of radiation. So, electromagnetic spectrum. Thermal radiation is a form of electromagnetic energy. Accordingly, it exhibits the same wave-like properties as light or radio waves. Each quantum of radiate energies has a wavelength lambda and a frequency v associated with it. The full electromagnetic spectrum includes an enormous variety of energy-bearing waves, of which heat is only a small. So these are the other different types of electromagnetic and thermal energy or its wavelength. Black body. The model of the perfect thermal radiator is so-called black body. This body absorbs all energy that reaches it and reflects nothing. If we possess infrared vision, a black body will glow with color above which is temperature. Perfect radiators are black in the sense that they absorb all visible light and all other radiation that reaches them. A perfect radiation will look black unless they are hot enough to radiate heat in the form of visible light of the flame. So, conventional device for approaching this idea is called the German term Hohlraum, which is hollow space. And this device traps all energy that reaches the aperture. So this is how it looks like. And usually kept at a constant temperature because the black magnetic radiating body E times dW over m squared. The symbol E, subset of lambda, lambda net T, denotes the distribution function of radiative flux in lambda or the monochromatic emissive power. So E, subset of lambda of quantity lambda and T is equal to dE, quantity lambda into all over d lambda or E times E and E times quantity lambda T. So this is Stefan-Boson law. So E subset of B multiplied by T or with O T to the power of 4. So T is the absolute temperature. O is always 5.67 0374 times 10 to the power of negative 8 Wm squared times kinetic to the power of 4, or 1.714 times 10 over 9 BTU over HR times F to R to the 4th. So radiant heat exchange. Suppose that heated object radiates only to some other object, radiates only to some other, and that both objects are thermally black. All heat leaving object 1 arrives at object 2, and all heat arriving at object 1 comes from 2. Thus, the net heat transferred from Q2 to 1 is equal to A subset of 1, E subset of B, and T subset of 2. So, Q net is equal to A subset of 1, E subset of B, quantity T subset of 2 minus A subset heat 3 subset of 2 is equal to A1, take A subset of 1 I O T subset of 1 to the power of 4 minus 2 T to the subset of 4 to the power of 4. The first object sees the other objects in addition to objects given a view factor f 1 to 2 must be included to the equation. Uh, U net is equal to a sub 1 f sub 1 to 2 so quantity T14 minus 2T124. You may regard f to the f subset of 1 to 2 as the fraction of the energy within one object that is intercepted. So this is an example. So a black thermocouple is inside a chamber with a black wall. If the air around the wall at 20 degrees, the wall at 100 degrees Celsius, and the heat transfer coefficient between the thermocouple and the air is 75 over m squared. What the thermocouple will. So the solution is the heat convected away from the thermocouple by the air and the air must be exactly balanced or radiated to it by the hot walls in the system in steady state. Furthermore, F subset of 1 to 2 is equal to 1 since thermocouple radiates all its energy to the wall. So the equation is constant HA, subset of Tc, quantity Tc, T subset of Tc over minus T subset of air minus Q net is equal to negative A subset of TCO quantity TC4 minus T wall 4 or the T subset of TC in Celsius. So 75 times T subset of TC minus 20 Wm squared is equal to 5.6704 times 10 to the power of negative 8 quantity 100 minus 100 plus 273 to the power of 4 minus t to the power of tc plus 273 to the power of 4 W over m squared. So since t is for radiation, that means shall be trial and error in the solution of this equation with t subset of Tc is equal to 28.4 Celsius. So that's it for this chapter. Thank you.